Okay, so the topic which I am just going to cover in this session is called trie structure. Okay, so we have discussed a number of tree structures, starting from the general tree and then the binary search tree, AVL tree, D tree, and we are going to add one more tree into that category group. In fact, this is going to be our last tree in the syllabus, which is called the trie structure. So the trie structure is going to be a slightly modified version of the binary search tree. So we have seen that binary search tree can be modified into AVL tree by making it a balanced. And so similarly, the trie structure is also going to be a kind of binary, but it's not going to have the characteristic of binary search tree like AVL, but it is going to be used for the same purpose. So only the similarity between binary search tree and the trie structure is that both the trees are going to be used for searching of values. That is a similarity, but the similarity ends with that. So trie structure is going to be completely new and different. So before understanding the characteristic of the trie structure, I feel it is more important for you to understand the purpose of the trie structure. See, the purpose of a trie structure is that uh, in some of the search, binary search is generally used for search. So when you want to store large volume of information, which needs to be searched frequently based on the key value. So in that case, you will use the binary search tree to represent them, or an AVL tree uh, or B tree. So searching is what we generally perform on a binary search tree. But sometimes the search could be done slightly differently. For example, I don't know how many of you have searched the words in dictionary. That is a digital dictionary. How they are generally implemented is that the moment you press one character, immediately the logic behind it will will recognize that the word for you're going to search for starts with that particular character. So it will exclude all other characters. That is, the first letter is now fixed. For example, let us assume that I type A, which means that the search is only needed among the words that all start with the A as the, I mean, or they all have A as the prefix. So it does not, it is not necessary to include all the words that start with the B, C, D, or up to Z. So now the first letter is found. Next, when I type the second letter, it will do the same thing. Let's say I type AC. What will happen is that now it will segment all the words that have A and C in order. So every time the the result will be reduced. The size of the resultant words will be, or possible words will be keep reduced. So initially, the entire collection of words were a possibility, and then when I typed A, out of that, a small group starting with A alone becomes a possibility. After that, when I type the second word, it's even narrowed down. So it's now going to be only words that have A followed by C are possibilities. Finally, when I type the last character, I would have reached the actual word. But if that word is not in the dictionary, then the search will be unsuccessful. So this is the basic characteristic of a dictionary. So that kind of a search is sometimes needed. Similarly, let's say I want to search for, I mean, I think you have a very familiar example which I just missed. So contacts, searching for contacts in your mobile phones. So if you take the mobile phone and you want to search for somebody's name, the moment you type the first letter, immediately you will see the list of all the names that all start with that particular letter. Similarly, when you type the second letter, it will list all the names that have the two letters together. So finally, it will show one particular name whose name is exactly what you are searching for, or you may never find that particular name in the contacts. The same mechanism is what we are now discussing about. So sometimes the search needs to be conducted at the character level. So you don't want to search for a single key. You want to search for a multiple character combination of or sequence of characters. So in that case, we have the idea called the lexical search tree, which will be then modified into a trie structure later. So lexical search tree is going to be used for searching when you don't want to search for the entire key, but want to search for sequence of characters. So here in the lexical search tree or the trie structure, the key is actually distributed across the different levels. Whereas in the binary search tree, each node contains a unique key. So in a normal binary search tree, each node contains an entire key and they are unique and they are independent. But here what happens is that the single key gets distributed across multiple nodes. So you will start from the root. From there you will identify where to go move in the second level. Then you will decide where to move in the third level. So in that way you will reach the leaf which contains the actual string. All the descendants of a node have a common prefix of the string associated with that particular node. So, for example, if you have that, okay, this is an example of a lexical search tree. So, the first node contains all the alphabets from A to Z, which means 26. Each node has 26 characters. Now, if you are trying to search for a word that starts with the A, you will come here and use the pointer to come to the second level. Whereas if you are trying to search for a word that starts with B, then you will use this particular link and will reach this node. And then after that, you will think of the next letter that is there in your word, and accordingly you will follow the path. Let's see. Let us assume that you are searching for a particular word which is not in the dictionary. For example, in this example, they have got AAA, AAZ. Let's say I want to search for AAP. Now, what will happen is that you will check whether A is present in the root and it is present. That means it's not null. So you are going to come to the next level. Next, you want to search. You will search for B, but B is actually not having a link in the second level, which means that the word you searched for, that is AB, ABC, which is there not in the this particular structure or lexical search tree, since B is null in the given implementation. So in this way, you will identify the sequence of characters which are present in the particular lexical search tree. So, and you will also identify the sequence of characters which are present in the particular lexical search tree. So in this way, you will be able to search for a particular word. So, to which slide I was able to explain to you. Uh, Raghavendra, ABC slide. Okay, let me just quickly resume the discussion. So this is what I was explaining you. Okay, I think now the PPT is visible to you. So this is what I was explaining, that this is a lexical search tree. So this particular tree is used for searching uh, combination of characters, not unlike the binary search tree where we always search for individual keys. Here we search for combination of certain characters, like for example the dictionary or the telephone directory where or the mobile phone contacts. So this is the idea of a lexical search tree. Now the problem with the lexical search tree is that you can see that it's going to have too many levels, because in each level you need to represent 26 characters. So the first level will have 26 links, because pointers, because these are all possibilities. In the second level you need to have 26 into 26 nodes, because A will have all possibilities like AA, AB, AC up to AZ. Similarly, B should have all the 26 combinations like BA, BC, BB, BC up to BZ. So as a result, in every level, the number of nodes required will be increasing. And as a result, the overall lexical search tree will be huge. It's going to be taking a lot of memory, and also the search time will also be excessively very high. So we are now going to slightly adjust this to make it into something called as a trie structure. So the problem with the lexical MA tree is that after a few levels, it becomes very large. And to prevent this, we use the technique of pruning the tree. That is, we cut all the branches that are not needed. For example, in this particular example, we don't have any word that okay, for example, A2, okay. So AB, there is no word that is that is a combination of AB. So we can avoid all the empty nodes, so that we will only have the branches and the nodes which will be containing actual data. I'll show you that tree. So we identify a pruned branch with a null pointer. For example, if no key starts with the letter X, then at level 0, the X pointer is null. So here what happens is that even if you don't have any combination for Y, you will still be having the link to Y, because this is built on as a template, as a common template. So whether you have actual elements or not, all the links will be there in the tree. But in the trie structure, you will only have links for which there are actual words. Otherwise, they will be having null pointers, and you don't need to represent them in the subtrees. You don't have the subtrees for that particular node. So I think I can show you the tree to make it understand you this. This is what we are referring as a trie structure, and we use the application called the spell checker. So the spell checker is kind of dictionary, but unlike a dictionary, we don't find the meanings here. There are no meanings or definitions available. It only tells whether a particular spelling is correct or valid. So this is the application. And now how this is different from the lexical search is that, see, for example, here we have the see, for example, from A to to the next level, there is only word that starts with the C. So we have just kept the remaining pointers to be null values. That is, A to A is null, A to B is null, and A to E is also null because we don't have words represented in our spell checker with that order. So we just keep it null, and we won't have the subtrees for that nodes. So we don't need to have all the subtrees for every combination or sequence. Only the sequence that is actually present will be filled with the address, and then it will continue like this. So the number of entries will be minimized under a trie structure comparing to a lexical search tree, because a lexical search tree is going to represent each and every possible combination irrespective of whether that word is going to be available in the dictionary or not. But here this will be including only the actual words that are represented, and the remaining will be just filled with the null values. This is the major difference between the two. Now, okay. Now, how to make use of this one? So, how to make use of this trie structure? Let us say I want to search for a particular word, and in my opinion, that word contains the letters A, C, E. Okay. So, let's say I want to search for a word whose spelling is ACE. I want to check whether such a word is in the spell checker. So I will start with the first node. I'll check whether A is null or not. If A is null, which means that I don't need to search for the remaining characters in that word because the first letter itself is not present. So I will end the search here itself. But here A is not null, which means that I can try to another level. So from A I come to second level. Now I have to check whether C is null or not. Again, C is also not null, which means there is still hope. I may find that particular word. So what is the next word letter I need to search for? ACE. So I will now check whether E is null in the next level, third level. And since E is also not null, I come to this particular node. And here I locate ACE at the leaf level, which means that that particular word is actually present in the dictionary and my spelling was recognized or uh, accepted as correct. Let's now try for some word which is not in the tree. Let us take the case of um, ACT is also there. AC. Okay, let us take ACB. So ACB is what I want to search for. So I will start with A not null. So I will come to the second level. C is also not level. But when I come to this level, I find B to be null, which means that there is no possibility of ACB to be found in this particular tree. So it is an invalid word. This is a simple idea. You can search, verify whether a particular word, the combination of a particular set of characters is actually represented in your spell checker. So this particular idea is what elaborated in the slides, and the trie structure is actually a short form of retrieval. So retrieval is what is shortly called as a trie. So that's the implementation we saw was for a spell checker, and it's meant for checking whether a given word has correct spelling according to the uh, the trie structure. To demonstrate this idea, okay, so we have used these alphabets. Our example was not for all the alphabets, we just used it for A, B, C, E, T. So it was a small a tree. In your exam you may be asked to construct a, okay, what kind of question you should expect in this particular topic. You may be asked a question saying that assume that these letters are included in the dictionary or the spell checker, and these words have to be included into that particular trie structure. So just like in this example, we saw that these are the words that are actually represented: A, EAT, ATE, PE, TAB, like that. You may be asked to represent some of the words in that particular in the implementation you are going to provide in the paper, and accordingly you must establish these connections. For example, let's say your example says that you need to include the word called BAT. Is it already there? Okay, it's not there. So BAT, which means you have to connect B with this particular node, and then you have to make this to be not null. So right now A is null in the second level because there is no word that is having the combination of BA. But now when you want to include BAT, you have to now make it not null and extend it to the next level. And in the next node, you have to make T to be null, not null, and then include the word BAT in that particular node, like the as a leaf. So likewise, you may have to construct here a trie structure for the given example. And there is only one algorithm available for this topic, which is search. So the search is very much like how we did. So we start with the root, and if the root is not null, then we proceed to the next level. And in case if you reach the actual word that you searched for, that is, if root entry equals the word, then your search ends there. See, the root is at every moment, whichever node you are currently in, that is called as a root. It's not about the root that is only the first root. Say, for example, initially when you start the search, this is treated as a root. From here, if you come to this node, now this becomes the root. So likewise, at every level, the current node is treated as a root. So, for example, when you want to search for ACE, and the moment you reach this particular node, this condition will be true. Root is equal to word. So it will return true. Otherwise, you will have to search further. But another question is that if the word is not at all found in the trie structure, how will you know it? Because if it is there, it will end at some point. This condition will end the loop when the word is actually located. But how do you know that it cannot be located? That is, you have to use the second condition. So the word length, if you have reached a node which is larger than the length of the word you are searching for, which means that that word has no chance of being present in this particular spell checker. So the length is greater than the word length, which means you have exceeded the length of the word and you cannot find it. So that is what the idea of this the algorithm. And one more point I need to add is that, uh, say for example, I think I already it's already included while I explained. For example, I want to search for uh, e, let's say ECA, okay, something like ECA. See, actually, you have that word in the dictionary, that is ECA. You have the words in the spell checker, but they are not connected. So the connection is what makes whether a word is present or not. So if when you are trying to search for a word, only if you find that particular letters to have not null values, then you can treat them as the valid words. But if they have null, if they are filled with the null values, then they are not present in the spell checker. I hope you were able to understand the explanation I gave. Let me just confirm whether anybody have doubt to clarify on this. I'm just asking, was it clear whether you were able to understand that idea of the trie structure? Am I audible? Sivanarayan,
Yes,
yeah, this yes sir is for audible, or is it for you were able to understand the topic I explained? Why no one is replying or responding? You understood. And what about others? Have you all just connected your mobile phone and kept it aside? Sai Prashant. Okay, sir. How did EAT come there? I'll show. Okay, EAT. See, you come to the first node, check whether E is null. It's not null, so you have a chance. So you come to from E, you take to this node. Here you check for A, or you check whether A is null or not null, and that is also null. So we have got the combination of EA, and from this, okay. So that is a good question. I forgot to include it. See why how straight away EAT has been included here is that there is no other word that is having the combination of EA. For example, here we have got a ACE, ACT, which means that you have to keep them separate because after you reach C, you may either go to ACE or you may want to go to ACT. So there are two options. But here in this case, the only word that is there with the combination of E and A is the EAT. So they have just included in the previous level. Instead of adding one more level, they just have completed it in this level itself. So that is a point. In every case, you can see that there are words that are having multiple possibilities. So there is a CAT, CAB. So that is the reason that EAT has been here itself. It is provided. Otherwise, it would have been having included with one more node, and under that EAT should have been provided. It is mentioned somewhere in the PPT itself. Uh, I haven't included the PPT, but that is the answer for that question. Okay, I said I finished my the lecture, and you can leave the session. The recording link will be shared soon along with the PPT.